Okay. Now, yesterday we are taken the necessary and sufficient current for a subgroup theorem one we are already taken that indicates a non-empty set H of a group G is a subgroup of G if and only if A comma B belongs to H means A B inverse is also belongs to H that are already taken. And in some of the cases we are using the same to prove the group means just you are using this and you are writing the same. That means instead of proving the four properties, just you are proving A B inverse belongs to H so that A comma B belongs to H. Then you are saying that is a group. Okay, now the second theorem is already discussed that. Now let G be a group, H be a finite non-empty subset of G. Then H is a subgroup of G if and only if the first one is A comma B belongs to H, A B belongs to H. That is the closure law and respect to multiplication. A belongs to H means A inverse belongs to H. This is another type. Okay. That means instead of proving that G is a group, just you are proving these two results, then you are saying that is a group. Okay. Now the properties of subgroups. Properties of subgroups. The intersection of the statement is intersection of two subgroups is also a subgroup. Okay. Now here you are taking the proof H1 and H2 be two subgroups of G. H1 and H2 be two subgroups of G. H1 is a subgroup. Okay. Now here you are writing already you are taken theorem number 1 A comma B belongs to H means A B inverse is also belongs to H that you are taken. Here the same property you are using here because H1 is a subgroup. You are taking an element of A and B belongs to H1 and you are saying A B inverse belongs to H1 because H1 is a subgroup. The theorem 1 what you have taken that you are using here. Okay. Now the second one H2 is also a subgroup. H2 is also a subgroup. You are taking two elements. One is A belongs to H2, B belongs to H2, which implies AB inverse belongs to H2 you are taking. Okay. Now the first one here you see AB inverse belongs to H1 and here AB inverse belongs to H2. Now A belongs to H1, A belongs to H2, which implies A belongs to H1 intersection H2 you are taking. Okay. Now B belongs to H1, B belongs to H2, then you are taking B belongs to H1 intersection H2 you are writing. From 1 and 2, what we can write? You see already are taken there. A belongs to H1 intersection H2, B belongs to H1 intersection H2. From 1 and 2, you can write AB inverse belongs to H, AB inverse belongs to H2. Now what we can say AB inverse belongs to H1 and AB inverse belongs to H2. Therefore, AB inverse belongs to H1 intersection H2. Now, if A comma B belongs to H1 intersection H2, then you are saying AB inverse belongs to H1 intersection H2. Therefore, what we can say H1 intersection H2 is a subgroup of G. Subgroup of G that you are writing. Now, here the next one, I think here you got the idea here. Just you see A belongs to H1, B belongs to H1. Then you are writing AB inverse belongs to H1 because H1 is a subgroup. That's why you are writing here. There is a subgroup itself and it is a non-empty subset. Then you are writing AB inverse belongs to H1 and here A belongs to H2, B belongs to H2 because H2 is a subgroup. You are writing AB inverse belongs to H2 and then here A belongs to H1, A belongs to H2, which implies A belongs to H1 intersection H2. B belongs to H1, B belongs to H2, then you are writing B belongs to H1 intersection H2, and I already have taken that. You see number 1, here this is the one, AB inverse belongs to H1, and AB inverse belongs to H2, then you are writing AB inverse belongs to H1 intersection H2, okay. Now, what we can say H1 intersection H2 itself is a subgroup, because the property A comma B belongs to H1 intersection H2 means AB inverse is also belongs to H1 intersection H2. Now, the next theorem, the union of two subgroup is a subgroup if and only if one is contained in the other. The next theorem we are taking here. Here you see, first let H1, this is if and only if P then Q and if Q then P, then you have to prove this. Now, H1 and H2 be the two subgroups of G. Two subgroups of G. Then what we have to prove here? If P then Q are proving here, H1 and H2 are subgroups means you have to prove one is contained in the other we have to prove. That is one group is contained in the other we have to prove. That means suppose here you are taking H1 is subset of H2, H2 is subset of H1. Then what you have to prove? You have to prove the union is also a subgroup that you have to prove here. Okay, here you see H1 is subset of H2 and H2 is subset of one is contained in the other. Then H1 union H2 equal to H2 or H1 because you see union means here if the that may be contained in either in H1 or either in H2 because H1 is subset of H2 means H2 is the bigger one. That's why you are writing here H2 and H2 is subset of H1 means you can write that is equal to H1 because H2 subset of H1 means H1 is a bigger one. That's why you are writing here H1 union H2 is equal to H2 or H1. Now, since H1 and H2 are the subgroups, we are already taken there. The union H1 and H2 are subgroups. That's why here H1 union H2 equals the result is you are getting H2 or H1 you are getting. Other are taken H1 H2 are the subgroups. Therefore, you are writing here H1 union. You are writing here H1 union H2. That's why H1 union H2 is a subgroup. Now here, suppose H1 union H2 is a subgroup. H1 is a union is H2 is a subgroup. Then what we have to prove? If Q, then P we have to prove here. That means if this is a subgroup, union is a subgroup, then we have to prove one is contained in the other. That we have to prove here by taking this. Now you take to prove that H1 is subset of H2 or H2 is subset of H1. The meaning of this is one is contained in the other. If possible, H1 is not subset of H2 and H2 is not subset of H1. That you take if possible. That is here you are right taking this not subset of H2, this not subset of H1. That means the first one, if you take here, there is an element, there exists an element S belongs to H1, the same does not belongs to H2. That is number one you are writing here. And H2 is not subset of H1 means there exists an element T belongs to H2 that is not contained in H1. That you are writing here. Okay. Now this is 1 and this is 2. Now from 1 and 2, yes, you can write S belongs to H1 union H2 you can write, because you see S belongs to H1, S belongs to H1 and T belongs to H2 is there, you can write S belongs to H1 union H2 or T belongs to H1 union H2 you can write. Now already you are taken, what is that? H1 union H2 is a subgroup. You can write here ST equal to K belongs to H1 union H2. Okay, H1 union H2. ST equal to K belongs to H1 or H2. ST equal to K belongs to H1 or H2. Now ST equal to K belongs to H1 or H2. Belongs to H1 or H2. ST equal to K belongs to H1. T is equal to, if you shift this S to other side, you get S inverse K belongs to H1. But here you see, here what you are getting, T belongs to H1. But here you see number 2, T does not belongs to H1. But here you got the contradiction. You got the contradiction. Therefore, our assumption H1 is subset of H2 and H2 is subset of H2 is wrong. That means H1 is subset of H2 or H2 is subset of H1. That's why the result if Q then P is 1. Now just you see here, you are taking, actually this is you are proving by using the contradiction method. Contradiction method means what we have to prove. If P then Q you have to prove. Q you are taking, Q if Q is not true, then you have to prove you are getting negation P, then you can say if P then Q that you are proving. That the same here, this is called the contradiction method. Okay, here what you are getting, this is by contradiction method. Okay. Now the next one, if H is a subgroup of G and H1, then H inverse is equal to H. That you have to prove here. Okay, H is a subgroup of G, then you have to prove H inverse is equal to H. Since H is a subgroup, for A belongs to H, A inverse is also belongs to H. Why it is not? Why you are writing means H is a subgroup means it is a group itself and it is a subset of G and the binary operation is same. And here you see A belongs to H means the inverse is also existing because H itself is a group. Therefore, you can say A inverse belongs to H. Here, if you take A inverse belongs to H, which implies inverse of inverse, if you take on both sides for this, you will get here A belongs to H inverse. Now, you see, you are taken here A belongs to H, the same A is also belongs to H inverse. Now, what we can say? H is a subset of H inverse because the same unit A belongs to H implies A belongs to H inverse. Now, here you see H is a subgroup. It must contain the inverse of each of its elements. Okay, H is a subgroup. It must contain inverse of each of its elements. Therefore, you are writing here H inverse is subset of H. Now you see number 1, H is subset of H inverse is subset of H. Now already you know if A is a subset of B and B is a subset of A, then you can write A is equal to B. By using that one, here you are writing H inverse is equal to H. Okay. Actually here you have to put H inverse equal to H, but here you are taking A is subset of B and B is subset of A, then you are writing A is equal to B. Now the next one, for any subsets H and K of a group G, the next one you are taking here H and K of a group G subsets, H and K are subsets of a group G. HK is a subgroup of G if and only if HK is equal to KH. HK is equal to KH. Now, here you are taking what? If HK equal to KH, then what we have to prove? HK is a subgroup, that we have to prove. We have to prove HK is a subgroup. That we have to prove. To prove that one, here you are taking, here to take the element that containing X belongs to HK. Okay. If Q, then 3 you are proving here first. HK equal to KH, then you have to prove HK is a subgroup. Now you take an element. Okay. HK is a subgroup of G. HK is a subgroup of G, that we have to prove. Already you are taken theorem number 1. You see there, if you take A belongs to that HK, that is X comma Y belongs to HK, means you have to prove X Y inverse is also belongs to HK, or you can say X Y belongs to H. You are taking X belongs to HK here, and X is equal to HK. You see H is an element of H. The capital letter H is a subset, and K is a small letter H is a subset of, that is H contains the capital H contains the small letter H. H is an element and this H is the subset, and K is an element, K is a subset. Similarly, X is equal to HQ you are adding here, Y belongs to HQ means Y is equal to you are taking H dash and K dash. Of course, H dash belongs to H, K dash belongs to K. Now, if you take XY is equal to XY is equal to, you see X is an element of HK, Y is an element of HK. If you take XY here, you can write HK into H dash K dash, that you can write as H into KH dash K dash, that you are writing as 1. Now, you see KH dash belongs to KH. KH dash belongs to KH. Okay. Then you are writing KH dash is equal to H2K2, because KH is equal to HK. Here you can write KH dash is equal to H2K2. You are taking some elements. KH dash belongs to this KH, and which is equal to H2K2 you are writing here. Now XY is equal to already you are taken there. What is that? Here you write XY is equal to H into H2K2 K dash. H2K2 K dash. Okay. XY you are writing here. This is XY. You are already taken this. You see number 1, XY is equal to you are writing here. X is the element of here. HK you are writing here. HK, and then this is H dash K dash, that you are writing as H into H2 K2 into K dash, that you are writing as H2 K2 K dash belongs to HK. Okay. Now here you see for X comma Y belongs to HK, XY is also belongs to HK. That is HK is closed we are writing. Okay. Now X inverse is equal to, here we are writing X is equal to HK. You see here you are getting here X is equal to HK. That inverse if you take, if you apply the reversal law in groups, you are getting here K inverse H inverse belongs to KH, which is equal to, already taken here KH is equal to HK. KH is equal to HK. That's why you are writing here K inverse H inverse belongs to KH is equal to HK. Now K inverse belongs to, sorry, X inverse belongs to HK. Now for X belongs to HK. Now what we can say, HK is a subgroup of the, by theorem number 2. What is the theorem number 2? Already I am told to you. Either you can use theorem number 1 or you can prove theorem number 2. What is the second one? You see there already taken that XY. This is number. You see the theorem number 2. Theorem number 2. You see here instead of A and B you are taking X and Y. X comma Y belongs to H means you are writing XY belongs to H. Here X belongs to H means X inverse belongs to H. The same this you are used there. Okay. Instead of, I am already told to you, instead of proving the 3-4 properties, just you can prove the either this first one, that is AB belongs to H, you can write AB inverse belongs to H. And the second one is you are taken B belongs to H means AB belongs to H, A belongs to H means A inverse belongs to H. Now we are using this one. Theorem number 2 we are using here. Theorem number 2 we are using here. Okay, here theorem number 2 we are using, and here you are writing the same here. X belongs to is the same here. XY belongs to HK, X inverse belongs to HK. Now what we can say, HK is a subgroup of G. And you remember the converse part is here you can take. Suppose HK is a subgroup of G. Suppose HK is a subgroup of G. Then what we have to prove? We have to prove HK equal to KH. That is, if P then Q are proving here. If P then Q. You see the statement there are proving the same. Now HK equal to KH. Just like in the previous case, what are taken, the instead of proving A is equal to B, you are writing A is subset of B and B is subset of A, you are writing. Here you see HK is a subset of KH, KH is a subset of HK, because A is equal to B means you can write A is subset of B and B is subset of A. Okay. Now HK is a subgroup. HK is a subgroup. HK is a subgroup. Here you can write H belongs to H. HK is a subgroup. then you have to prove Hk is equal to Kh, that you have to prove. Okay. Now Hk is a subgroup, means you take any one element, that is H belongs to H, K belongs to H, means you can write H inverse, K inverse belongs to Hk you are taking here. This is by convenient you are taking here. What you have to prove means here, just you see, you are taking an element belongs to that Hk, the same is also belongs to Kh, or the same, you are taking an element of Kh and is the same belongs to Hk, then you can add this. Now here you see H belongs to H, K belongs to K. H inverse, K inverse is also belongs to H because H is a subgroup. Now you take the inverse of that. You can write here H inverse, K inverse of inverse is also belongs to it because HK is a subgroup. The inverse is also existing in HK because there is a subgroup, it is a group. Therefore, the inverse is also existing. Now, if you apply the reversal law in groups, you can write here K inverse of inverse is the same. H inverse of inverse is also the same. You are writing KH belongs to HK. KH belongs to HK. Now you see here, okay. Now here you are taking here HK is a subgroup, that by using that one here you are writing KH belongs to HK, and here you are writing KH is any element of KH, okay, but KH is any element of HK. Now what are taking here? KH belongs to KH belongs to KH. The same KH is also belongs to HK. Therefore, what are you writing? KH is a subset of HK. KH is a subset of. Okay. Now here the next one what are writing means, you see HK is a subset of KH is a subset of HK is over. Now you have to prove HK is a subset of KH, because you have to prove A is equal to B means A is subset of B and B is subset of A, that you have to write. Now you take an element of HK, that means you are taking X belongs to HK. Now the same you have to prove that belongs to KH, then you can write HK is a subset of KH. The same you are writing here, X belongs to HK, you are taken X inverse belongs to the HK, because HK is a subgroup, the inverse is existing, that's why writing X inverse belongs to HK. Now you take an element of that HK, X inverse is equal to HK, inverse of inverse you are writing here, take the inverse on both sides, you'll get here X inverse of inverse is equal to HK inverse, okay. Now inverse of inverse is the same one, and HK inverse is equal to K inverse H inverse, because inverse law, reversal law in groups you are writing here, K inverse H inverse belongs to KH, because K inverse is an element of K, H1 inverse is an element of H. Now what are taken here? X belongs to HK, the same X is also belongs to KH. That's why here you are writing HK is a subset of KH. Here you are writing HK is a subset of KH. Already you are taken here KH is a subset of HK. Now what we can write? HK is equal to KH, because A is subset of B and B is subset of A, then you can write A is equal to B. That's why here you are writing the HK equal to KH. Now the proof is over. Now the next one, you see a subset H of a group G is a subgroup of the if and only if H inverse is equal to H. Now first we are proving here the if Q then P you are proving here. Q is here, H inverse is equal to H, then you have to prove H is a subgroup. That you have to prove. Our aim is to prove H is a subgroup. Already you are taken subgroup in the sense either you can prove by theorem number 1 or you can prove by theorem number 2. Theorem number 1 is what? A comma B belongs to H means AB inverse is also belongs to H. That is the theorem number 1. By using that here, you are writing the same here. And then here you see, here first what I have taken here to show that H is so that we have to prove. Now, A comma B belongs to H. You take the arbitrary elements belongs to H. Now, B belongs to H implies B inverse is also belongs. You raise the powers by -1. That is inverses you take on both sides. Now, A belongs to H, B inverse belongs to H inverse. Now what we can write? AB inverse belongs to H inverse, because you see A is an element of H, B inverse is an element of H inverse. Therefore, you can write AB inverse belongs to H inverse. Now already you see what you got here. H inverse is equal to H. Therefore, you can replace this H inverse by H. That's why here writing AB inverse belongs to H. Now by theorem number 1, what we can say? H is a subgroup of G. H is a subgroup of G. Now if Q then P is over. Now if P then Q, that you have to prove. Now what is given if P then Q means H is a subgroup of G, then you have to prove H inverse is equal to H. That you have to prove here. Already you know A is equal to B means you can write A is subset of B and B is subset of A, that you can write. The same here you are written. H inverse is subset of H and H is subset of H inverse. Okay. Now AB inverse belongs to, you take an element belongs to H inverse, H inverse, and then here you prove the same is also belongs to H. Just like in the previous case, you are taking here just to take AB inverse belongs to H inverse, the same is also belongs to H, then you can say that is H inverse is a subset of H. Now just to take A belongs to H, B inverse belongs to H inverse, B inverse belongs to H inverse means you raise the powers by inverses so that you get B belongs to H. Now here A belongs to H, here B belongs to H, which implies here you can write AB inverse belongs to H, because H is a subgroup, because H is a subgroup. Now here you see AB inverse belongs to H inverse, the same AB inverse is also belongs to H. Therefore what we can say, H inverse is a subset of H, is a subset of H. Now here one portion is over. You see here H inverse is subset of H is over. Now to prove this is equal to this H inverse is equal to H, you have to take an element belongs to H. The same is also belongs to H inverse. Then you can write H is a subset of H inverse. Okay. Now to prove that one, you take an element that belongs to H. Here the arbitrary element you have to take. A belongs to H. You are writing here. You write A into E inverse belongs to H inverse, because this is by convenient. This is not, there is no need to write a the same fashion. But here you see this is you are taking by convenience. There is no need to confuse here. Just to see here E is an element of H. E inverse belongs to H inverse. We are taking some element. Okay. E inverse belongs to H inverse, and if you remove the inverses, you get E belongs to H. You can write. Okay. Now E inverse belongs to the same. Now E inverse is what? E inverse is the same you will get, because the identity element inverse means you get the same. E belongs to H inverse. Now what we can write? AE belongs to H inverse, AE equal to A, because the identity element means you get A dot E equal to A, you are getting here A belongs to H inverse. Okay. Now what you are taken here, A belongs to H, and the same A is also belongs to H inverse. Now what we can write, H is subset of H inverse. Now what we can write here, you see H inverse is subset of it. Now here you are writing H is subset of H inverse. Now which implies H inverse is equal to H, because this is A is subset of B, this is B is subset of A. That's why you're writing here A is equal to B means the same you can add there. Now the proof is over. This is the way you have to prove. Okay. Now just to concentrate, just to you see first what you have to prove, what they are given in the data, and what you have to, that we have to keep it in mind, and then according to that you have to write. And don't get confused here. The what data they are provided and what you have to prove, that you have to keep it in mind. That you have to, and you have to proceed as like the previous case, just like that. Now integral power, the next one is integral power of element. Already power means you can say base and base and power is there. You see, let G dot be a group, G dot be a group, and dot is a binary operation, dot is a binary operation or multiplication. Now let A belongs to G, then A dot A, or A into A, A into A into A, A into A into etc. elements of G. Okay, etc. A is the element of G. Then if you multiply A with A, how many times, whatever it may be, A square, A cube, A to the power 4, whatever it may be, here you are getting here A to the power n equal to A, so on to n times you are getting here. Now that A to the power n belongs to G, where n is any integer. Okay, n is any integer, A to the power n belongs to G, then this is called an integral power of A. That means A to the power n is called integral power of an element of A that belongs to Z. Okay, that means G dot is a group, A is an element of Z, so that A to the power n belongs to G, where n is any integer. This is called integral power of A. Okay, now the note. This is the definition. Okay, just should remember here, A is an element of G. If you multiply, how many times if you multiply the same is also belongs to Z, you will get here. Now the note. here you see E is the identity element of G. A to the power 0 is equal to E you are getting here. Okay, identity element of G means here you see dot is the multiplication. I'm already told to you. Whenever you got the plus sign, dot 0 is the identity element. Whenever you got the dot, you will get 1 is the identity element. Now here a to the power minus n you can write as a to the power n to the power minus 1, and you can write inverse of an is equal to a to the power minus n. A to the power m into a to the power n you can write a to the power m plus n, and already you know these are the laws of indices. You can write the same here. A to the b to the power n means a to the power n to b to the power n if G is abelian group. Now G plus is a group. You see in the starting you are taking G dot is a group you are taking here in the definition. Here the same can be extended to G plus also. Here A plus A plus A n times if you write you will get NA you are getting here. That is also integral power of A. That is also you can say integral power of, it is called an integral power of A. Okay. Either G plus means you will get here NA and G dot means you will get A to the power n. That is the case. Now here you see the definition of order of an element. You see the definition of an order of an element. You see, this is if G is a group, A belongs to G, the order of A is the least positive integer n, such that the order of A is the least positive integer. If n is n least positive integer, then A to the power n equal to E, so that you can write order of A is equal to n. Okay. First, what you have to take? Here G is a group. First case, A belongs to Z. That means A is the element of Z, and the order of A is given by n, where A to the power n equal to E. Okay, order of, that means you see here the n is the least positive integer, A is the element of G, E is an identity element, then you are writing A to the power n equal to E, then only you can write order of A is equal to n. Okay, this is the definition of order of an element of a group. If there exists no such integer, then A is of infinite order or zero order you can say. Okay, that means if it is not possible to get the value of n, so that A to the power n equal to E, that is called of, that is that A is of infinite order or zero order, that will be said. Now the identity is the only element of order 1. The identity is the only element of order 1. If there exists a positive integer m such that a to the power m equal to E, which implies order of A is less than or equal to m. Okay, that will be here. You see, I will see one problem. Okay, here just we will go through that, so that here find the order of each element of a multiplicative group. You see, this is what? This is the fourth roots of unity, is it not? G is equal to the set containing 4 elements. Of course, this is a finite group because the number of elements are finite. How many elements are there? Out of G equal to 4 here. Okay, because 4 elements are there, 1 minus 1, I minus I. Now here the solution, just you see here, you have to find out the order. Okay, now here you can write minus 1 to the power 1 equal to minus 1. Minus 1 square is minus 1 into minus 1 equal to 1. First one you see minus 1 to the power 1 equal to minus 1. You just you write here, 1 is the identity element, 1 is the, because dot is the binary operation, that's why here or 1 is the identity element, you can write order of 1 is equal to 1. Now minus 1 is there, you are writing minus 1 square equal to 1, because you see A to the power n equal to E means you are writing order of A is equal to n. Now minus 1 square equal to 1, that means order of minus 1 is equal to 2 you are writing. Now similarly, if you write I to the power 1, I to the power 2, I to the power 3, I to the power 4, you see I to the power 4 is equal to 1. Okay, now order of I is equal to 4, because I to the power 4 equal to 1 you are getting. Just like you compare this with A to the power n equal to E, already you have taken the definition. You see the definition what I have taken. A to the power n equal to E means order of A is equal to n. Now this is a multiplicative group, means this is fixed one. E equal to 1 is a fixed because multiplicative group. And here I is also fixed. Only you have to raise the powers by 1, 2, 3, 4, so on. So that here I to the power 4 means you are getting here 1. Therefore order of I equal to 4. Similarly here also minus I to the power 1, 2, 3, 4. Here you see you are getting here 1. That means what we can say, this minus I is fixed element of that that G, and then here you see this is you are getting 1, therefore order of minus I is equal to 4. This is the way you have to write. Just like you see here, A to the power n means here A is equal to I, n is equal to 4. That's why you are getting here E equal to 1 you are getting, therefore order of I equal to 4, order of minus I equal to 4. Okay, that is, keep it in mind. Here